Hi everyone, this video is going to fill in the final details at the end of chapter 3. So what I want you to do is get your lecture notes and turn to the second to last page about halfway down, and we'll start there. We're going to compare the sizes of atoms and ions. And doing that comparison requires that we think mostly about two important questions. What is the outermost shell? That's going to determine the size. And also, what is the effective nuclear charge? So when we think about the effect of the outermost shell, the thing that we have to remember is the lower or the smaller the outermost shell number, the smaller the atom or the ion is going to be. So as we move up in a group, the atom is going to get smaller. So as an example, if we compare the chalcogen group, oxygen with its outermost electrons, its valence electrons in shell 2, is going to be smaller than sulfur, which will then be smaller than selenium and tellurium. Sulfur's outermost electrons are in shell 3, selenium's in shell 4, and tellurium in shell 5. And we see that borne out in the measurement of the atomic radii of each of these elements. How does the effective nuclear charge then affect size? Well, we saw from class that as we move across to the right in a period, that's a row in the periodic table, the effective nuclear charge increases. The increasing effective nuclear charge then holds the electrons in more tightly, and that makes the atom or the ion that we're considering smaller. So farther over to the right means smaller atoms or ions. If we examine the atoms that are in period 3, beginning with sodium, we see that as we move to the right across the period all the way over to argon, we get smaller and smaller. And we can see that in this size comparison from your textbook. So let's fill in your lecture notes now, beginning with the middle part of page 16 down near the bottom. We want to know, how does the value of the effective nuclear charge change moving to the right across a period? We know that moving to the right across a period, the valence electrons are going to be held more tightly because the value of the effective nuclear charge increases. We also know that moving up in a group, the valence electrons are held more tightly because our valence shell is smaller and therefore closer to the nucleus. So when we think about the trends in atomic radius with regard to the moving across a period, atomic radius decreases, we said, and that's because effective nuclear charge is increasing. When we think about the movement up in a group, we see that because the shell gets smaller, atomic radius decreases. We see the very smallest atoms, therefore, in the upper right part of the periodic table. Helium is our very smallest one, and we see our biggest atoms in the lower left. When we think about the same ideas with regard to monatomic ions, one rule we can always remember is that cations are always smaller than the corresponding neutral atom. Let's look at an example. Here's sodium and its electron configuration with its valence shell composed of a single 3s electron. We see it here. Then we make the cation from it, and the only electron we take away is this 3s electron. And now we see that the outermost shell is shell 2. So it has to be true that the Na plus is smaller than Na because it has fewer shells. Let's look at a more complicated atom now that we might make a cation from. Here's lead. More complicated because its electron configuration is much bigger. Now if we think about just the outermost shell, lead has 2 6s electrons and 2 6p electrons. So lead has 4 valence electrons. However, if we take the outermost shell's highest n value subshell away, that would be 6p, and we make lead 2 plus, we see now lead 2 plus only has 2 valence electrons. And because there's only 2 valence electrons in lead 2 plus, there's less electron-electron repulsion, less electron shielding, and those 2 electrons in lead 2 plus can nestle in closer to the nucleus than the 4 electrons in lead can. There's more electron-electron repulsion there. So lead is larger, lead 2 plus is smaller. So when we think about the same ideas with regard to anions now, they're going to be made from nonmetals. Anions are always larger than the corresponding neutral atom, and the reason has to do with our explanation that we used for lead. Anions are larger than their parent neutral atom because with an anion we have more electrons in the valence shell, and the atom is going to be larger because those electrons repel each other. Look at oxygen, for example. The oxygen atom has 6 valence electrons, whereas the oxide ion with 2 more electrons has 8. There's going to be more repulsion, more valence shell shielding, and these electrons aren't going to be able to nestle as close to the nucleus as those electrons will. So our summary overall, for a given atom, an anion made from that atom is going to be biggest, then the neutral, and then the cation is going to be smallest. Summarizing the 3 factors: shell number, the lower shell number, the smaller the atom or ion. Z effective, the higher the Z effective, the smaller the ion, and we get higher Z effective by moving to the right across a period. And finally, if both the shell number and the Z effective are the same, then we can consider electron-electron repulsion, or what we call valence electron shielding. Let's try an example problem. So we've got 4 species that we're going to compare: nitrogen atom, nitrogen cation, a phosphorus atom, and a phosphorus anion. Immediately I think about shell number. The valence electrons in the N and N plus will be in the second shell. The valence electrons in the 2 phosphorus species are in the third shell. So automatically these 2 are going to be bigger than the nitrogen species. Now, between phosphorus and phosphorus 3 minus, we remember the anion is always bigger. So I think the P3 minus is my biggest. Next, I think we have P. And now we're going to try to decide between N and N plus. So I think N plus is our smallest because cations are always smaller than their neutrals. So N comes next, and N plus is our smallest. One more problem. Let's try a comparison between the potassium neutral atom, potassium cation, and the argon atom. And you might want to copy this set of this problem into the end of your lecture notes. We want to know who's biggest, who's smallest, and who's in the middle. First, let's write the electron configurations of each of these 3. Potassium ends with its valence electrons, a single one in the 4s. Then when we make potassium plus, we take away that 4s electron. So the outermost electrons now are in shell 3. And when we construct argon, we see argon ends up with the same electron configuration as K+. Outermost electrons in shell 3 and an identical configuration. So when I compare those 3, I immediately think that K is my biggest one with a larger outer shell. Next, comparing potassium plus and argon, what I notice is that they have exactly the same electron configuration as we said, and there's a name for that. Atoms or ions that have exactly the same electron configuration are said to be isoelectronic, a good vocabulary word. All right, so when you have isoelectronic species, we have to see who has the higher effective nuclear charge. If you look at the nucleus of any potassium atom or potassium cation, it's got 19 protons. 19 plus pulling those electrons in. If you look at argon, there's only 18 protons. So there's a greater nuclear charge in potassium plus, and that's going to pull the electrons more close and make potassium plus my smallest of those 2 final ones, with argon in the middle. I hope that helps you navigate the end part of Chapter 3 with atom and monatomic ion sizes.